Welcome back to the AI cost optimization series on human mimics. In the last episode, we built an exact response cache, a lookup table that returns the identical answer for the identical question with zero API calls on a cache hit. But here is the problem real users actually face. One user asks, "What is the capital of France?" A second user asks, "Can you tell me the capital city of France?" A third user asks, "Which city is the capital of France?" Three different strings, zero cache hits, three API calls. They are all asking the same thing, but an exact cache does not know that, and your budget does not care about the distinction. This episode, we fix that with semantic caching.
Now, let's compare exact caching with semantic caching. On the left, we have exact cache. It only returns a cached response when the new request is an identical string. Even a small wording change, like asking, "What's the capital city of France?" instead of "What is the capital of France?" results in a cache miss, forcing another LLM call. On the right is semantic cache. Instead of comparing words, it compares meaning. Although the two questions are written differently, they ask for exactly the same information. The cache recognizes that similarity and returns the existing answer immediately. The big idea is shown in the center. Same question, different words, same cache hit. This makes semantic caching faster because it avoids unnecessary model calls, cheaper because fewer tokens are processed, and smarter because it understands the user's intent rather than matching exact characters.
So unlike exact caching, semantic caching can reuse answers for near duplicate questions, dramatically increasing cache hit rates in real-world AI applications.
So what exactly is semantic caching? Instead of comparing two questions character by character, we compare what those questions mean. We do this using something called an embedding. An embedding is a mathematical vector, a list of numbers that represents the meaning of a sentence. Sentences with similar meanings will have vectors that are close together in what we call vector space. When a new question comes in, we convert it to an embedding. Then we search our cache for any stored question whose embedding is close enough. If we find a match above a similarity threshold, we return the cached answer. No API call needed. If we do not find a close match, we call the API, get the answer, store it in the cache for next time. That is the full loop, and it handles word variation, rephrasing, and even slight paraphrasing, all of which would fail in an exact cache.
Let me quickly explain the similarity metric, because it matters when you tune your threshold. We use cosine similarity. The formula is straightforward. We take two embedding vectors, compute their dot product, and divide by the product of their magnitudes. The result is always between 0 and 1. A score of 1 means the vectors point in the exact same direction. The questions are semantically identical. A score of 0 means they are completely unrelated. In practice, good semantic matches score between 0.85 and 0.99. Very different questions score below 0.7. In our demo, we will set the threshold at 0.85 and 0.60 to show tuning difference in similarity score. Any question scoring above that gets a cache hit. Below that goes to the API. This threshold is your main tuning knob. Set it too high, you miss valid matches. Set it too low, you return wrong answers for unrelated questions. We will come back to this in the code.
To understand cosine similarity, let's consider two sentences. Sentence 1. I love to play football. Sentence 2. I enjoy playing soccer. After embedding these sentences into a vector space, we get two vectors. For example, vector A could be 0.1, 0.3, 0.5, and vector B could be 0.2, 0.4, 0.6. To calculate cosine similarity, we used a formula cosine similarity equals the dot product of A and B divided by the product of the magnitudes of A and B. The dot product of A and B is 0.1 times 0.2 plus 0.3 times 0.4 plus 0.5 times 0.6, which equals 0.44. The magnitude of vector A is the square root of the sum of its squared components, which is approximately 0.374. Similarly, the magnitude of vector B is also approximately 0.774. Finally, we divide the dot product by the product of the magnitudes, resulting in a cosine similarity of approximately 0.51. This indicates a moderate similarity between the two sentences.
Let me put real numbers on this. Assume your application handles 1 million requests per month. In most production chatbots and support tools, between 20 and 40% of questions are variations of things that have been asked before. Let us use 30%. That is 300,000 requests per month that are semantically duplicate. Without semantic caching, every one of those 300,000 requests hits the API. At an average of 500 input tokens per request, that is 150 million input tokens. On Claude Sonnet 4.6, at $3 per million input tokens, that is $450 a month in completely avoidable input cost. And remember, when you avoid an API call entirely, you also avoid paying for the output tokens that call would have generated. So the total saving is higher. Semantic caching is particularly powerful for applications that serve many users asking similar questions. Support bots, FAQ tools, educational assistants, product recommendation engines. Anywhere user intent clusters, this technique pays off. Here is the full architecture, step by step. First, a user query arrives. We immediately pass it to a lightweight embedding model. In our demo, we use sentence transformers with the all mini LM L6 v2 model. This runs locally, it is free, and it is fast. The embedding model converts the query into a vector, a list of 384 numbers that encodes its meaning. Next, we search our cache. We compute cosine similarity between this new vector and every vector we have stored previously. If any stored entry scores 0.85 or higher, we have a semantic cache hit. We return the stored answer immediately. The Claude API is never called. If no match is found, we call the Claude API. When the response comes back, we store both the query embedding and the response text in our cache for future hits. The cache starts empty and fills up as real traffic flows through. In production, you would use a vector database like ChromaDB or Pinecone for persistence and scale. In our demo, we use an in-memory list, enough to see the full behavior. Let me quickly compare the two caching approaches so you know when to use each one. Exact caching is simpler. It is just a dictionary lookup. Zero risk of returning a wrong answer. But it only hits on exact string matches. One different word, and it misses. Semantic caching handles rephrasing, word variation, and even partial paraphrasing. The trade-off is a small setup cost. You need an embedding model, and a small risk of false positives if your threshold is too low. For customer support bots, FAQ systems, and educational tools where users phrase the same intent in dozens of ways, semantic caching wins. For systems where queries are highly structured and repeat verbatim, like tool calls or template-based inputs, exact caching is simpler and sufficient. In practice, many production systems layer both. Exact cache checked first for speed, semantic cache checked second for coverage. The threshold is the most important tuning parameter, so let me give you a practical guide. Start at 0.85. This gives you good coverage for rephrasings while keeping false positive risk low. If you find your cache is returning incorrect answers for different intent queries, raise the threshold towards 0.90 or 0.92. If your hit rate is low and you are confident in your data quality, try lowering towards 0.80. But go carefully. Below 0.75, you risk semantic drift where different questions start matching each other. The right threshold also depends on your domain. Technical queries, like API documentation or code questions, tend to be more precise in their embeddings, so a higher threshold makes sense. Conversational queries in natural language have more variation, and a slightly lower threshold performs better. Always log your similarity scores in production. Look at the distribution after a week of traffic. Your data will tell you exactly where to set the line. Hello. This is the lab part. In this lab, we'll show how to calculate semantic cache score based on the most method for similarity calculation, which is the cosine similarity criteria. Let's start. Firstly, here we loaded the needed APIs. Hot API keys is for our cloud models and for Hugging Face token. For Hugging Face token, we need it for loading the model used for embedding. This model used for embedding, its name is the All Mini LM L6v2. This model used for embedding. After this, we create a Chroma database. This database is needed to store the vectors generated by the embedding. And we determine the method criteria for the similarity calculations is based on the cosine. There are other methods, but the common one is the cosine similarity. Then we determine the similarity threshold. Here's 0.6. That means if the similarity is greater than 0.6 between two queries, now we mark this as cache hit. If the similarity is less than this threshold, we mark as cache miss. Let's see, what is the code example? Firstly, you define 5 different samples from user query, then start to query everyone. And after the query for everyone, I added the embedding. After the embedding for every user query, I added those that created Chroma database. Then for any new query, I make similarity score between 2 different users' query. Here's the output of this. For example, user query firstly ask about this: what is espresso coffee? It's because its already database is empty. So here is counting as cache miss because no or no any stored vectors exist. So we compare with empty. So here mark is as a cache miss. So the user starts for second query. He make explain espresso. For this query, he find the similarity score is 0.67. In this 0.7 is greater than threshold. We put it 0.6. So I make as a cache hit. Cache hits means I will not call API for respond about this query. Just I recall the cached reply from the old same similarity score for the old user query. Then, next query, describe the espresso coffee. Same issue. Now similarity becomes 0.9. That is greater 0.6, so is mark as a cache hit. Then the user here asks us question. That is far away. What are, for example, how many planets are in the solar system? This is a far away. So you can see similarity score is with negative value. And the score is less than 0.6, so is marked as a cache miss. If we show the database, our table is stored in the Chroma database. We find these columns items. First is the ID and the embedding, then document metadata and this flag and this timestamp. First user ask, what is the semantic cache? This is the user query. User's query is convert to embedding list of vectors using the embedding Hugging Face model. Then, this is the cloud answer. Here's the cloud answer for this user query. Also stores as a metadata. Then, because its initial and the vector of this is empty, say is marked as cache miss. Then the user asks a question, second one, who won the FIFA World Cup? This is far away, and far away from similar. They are at OK. In this case, firstly, it convert to embedding, and they make a similarity, calculate the similarity score, then give the score. Score will be less than threshold, so is marked as a cache miss. This last is the third query here. This query here, can you explain semantic cache in this firstly convert to embedding. Then after embedding, I calculate the similarity. And this is case, similarity will be greater than our target threshold, so we mark as a cache hit. And in this case, he didn't make API call. He just restore or answer with the same questions, with the most similarities that Cloud answered before. So here we can see the same answers for the first and the third one get the same answer without any API call. Before I wrap up, a few production considerations you need to think about before deploying this. First, persistence. Our demo uses an in-memory list. In production, use a vector database. ChromaDB works well locally with no cloud dependency. For cloud scale, Pinecone and Weaviate are the standard choices. Second, TTL, time to live. Some answers go stale. If you cache answers about pricing, availability, or current events, those entries need to expire. Add a timestamp to each cache entry and invalidate after a reasonable period. Third, embedding model. The local all-mini-LM L6v2 is excellent for English and runs with no API cost. If your users span multiple languages, switch to a multilingual model. If you want higher quality and can tolerate a small embedding API cost, OpenAI's Text Embedding 3 Small or Anthropic-compatible alternatives work well. Fourth, never cache user-specific or personalized answers. If your system prompt injects user context, account details, history, preferences, those responses are unique to that user and must not be returned to others. And always log. Track your hit rate, the distribution of similarity scores, and the topics that keep missing. Your cache data is a gold mine for understanding what your users actually ask. Let me recap what we built today. An exact cache matches on identical strings, powerful but brittle. Real users rephrase. Semantic caching solves this by matching on meaning. We use a lightweight local embedding model to convert every query into a vector. We store those vectors. When a new query arrives, we find the closest match in our cache using cosine similarity. If the score clears our threshold, we return the cached answer, no API call. At 30% semantic duplicate rate across 1 million monthly requests, that translates to hundreds of dollars in savings, just on input tokens. Output savings stack on top, and as your cache grows, the hit rate improves. The threshold is your tuning dial. Start at 0.85. Log your scores. Adjust based on your domain and your users. In the next episode, we move to the third and final technique in our call reduction layer, rate limiting per user. We will look at how to protect your budget from individual users generating disproportionate API load. If this was useful, hit subscribe, leave a comment with any questions, and I will see you in the next one.